Hello community! Welcome to AI Robotics 3. Now, in my last two videos, we were talking about PaLM-E, we are talking here about Vision-Language Model, and we are talking about VIMA, our multimodal LLM prompt for robotics. And let me ask you, are you really satisfied here with the robotics integration into our visual language model? No? Well, what a coincidence, because today we are going to talk about the latest development here, and it is called RT-2. Look, this is a robot that learns different tasks. And you might think, well, that's not really amazing. Yes, it is. Look, it moves back to Google. Google could be everything. And to differentiate what is Google is amazing. Let me show you. Of course, you guessed it, since there is an RT-2, there must have been RT-1. So in December 2022, you have here Google Robotics at Google, and Google Research and Google Brain. They published RT-1, and now at the end of July, we have RT-2, a vision language action model transfer web knowledge to robotic control. So what we do, we take advantage that we have here, well, some companies copied here the complete internet, the complete text and the complete images, and we have here an information source that we're gonna use now for the pre-training of our robot model. Let's start. You might think this is a little bit technical. It is not. It is so simple. Think about theoretical physics in the 17th century, Newtonian mechanics. So, what we have. If we have a single particle moving in a three-dimensional space, you have three translational degrees of freedom. This corresponds to the movement in the x, y, and z direction. And if you have an extended body, so not a point-like body, you have additional three rotational degrees of freedom. So either you rotate around the x, the y, or the z axis. So together you have 6 degrees of freedom, very simply. And you're not going to believe it. This is all. This is all we need to understand the latest technology development in robotics or embedded AI or however you want to call it. Do you remember here in the second robotics video, VIMA with our multimodal LLM prompts, where we had a textual prompt and some images, some pictures, how we want the initial condition or the end result to look like? Now, we simply extend this idea now to multimodal token that include now actuator for our robotic system. It is as easy as this. So, our multimodal tokens that we need now, they are simply a set of the human language token, of our sensory token, our visual token, our infrared token, our LiDAR image token, and now the robot actuator action token. So let me focus on number 3. What are robot action tokens? Yeah, we combine it. And hey, we just have, look at it at an abstract level. We just have tokens, and we have more tokens, and we have even more tokens. And we know a system that is able to learn from a sequence of tokens. Normally, we call it a transformer architecture. So we are absolutely familiar with this architecture and with this technology. We just add some tokens, and those tokens are robot action tokens. A beautiful, simple theory. So, we know how to find a sequence of token? Yes, of course. So here we go. You know that the human language token, those are our ChatGPT, our large language model that we have. It is great. In my last two videos, we extended now this idea to have here a visual language model. So we have the human token with the intelligence, or maybe even with a chain of thought, and all the visual tokens that we have if we combine speech and visual. And now you're not going to believe it. What we do here is we have here the visual language action model, where we simply add here the action tokens, and this is it. Now, our VLA system, or RT-2 for Robotics Transformer. And now you know what system we're going to use. We're going to use the transformer system, like in the Vision Transformer. We have now a Robotics Transformer, of course, cutting edge model, at least now, end of July 2023, that harnesses the power of a Vision-Language Model, of a VLM model here, and we're operating here with 55 billion free trainable parameters. And we want here to get control about the robot. A significant leap in the field of robotics, demonstrating that we can have here the web-scale pre-training, and I will show you this in detail in a minute, to be used to improve the generalization performance of a robotic system. So, very easy. We combine our LLM, plus visual token, and we combine our LLM and visual token and robot action token to a new AI system. You see, as simple as that. Now, what is the difference between VLM and VLA system? In general, VLM system generate address only the higher level aspects of the robotic planning, interpreting commands and parsing them to individual parameters, which are then executed by several low-level robotic controllers. So the command is, the output is move a little bit to the right with your robotic arm. Now, in stark contrast, a VLA model, like our RT-2 model, on the other hand, integrates now the Vision-Language Model directly into the low-level robotic control. We have a closed loop of images that are taken, let's say, about 3 Hertz. Our basic human knowledge, since this is a copy of the human internet, and then we integrate it with the closed loop real-time robotic control. So we see every 1/3 of a second what is the image, what has the robot done, and we have a control closed loop. Beautiful. What else? This robot actuator action token. Is it complicated? No, it is so simple. As I told you, you have 3 degrees of freedom here for translation in theoretical physics, and you have 3 degrees of freedom for rotational bodies. This is it. So you have 6 degrees of freedom, and you can move now your robot arm in any direction. Now, if you have at the end of this arm a gripper or a tool, you can have now a 7th dimension of freedom, like say the angle, how much this gripper opens up, or you have a sensor on the top, on the very top of the gripper. So it tells you, hey, you have to have a firm grip or a very sensitive grip. So you can have 6, 7, 8, 9, 10 dimension of freedom, depending on the tool you have on your robotic arm. You see, it is so easy to extend here additional tools here to our robotic control system. Now, since we are here not in theoretical physics where we calculate everything in perfect continuous vector space, but we are here in computer science, we do approximations. Yes, our computer programs should end within a limited time span. So we go from a continuous action span to a discrete approximation. Very easy. So let's say the arm of a robot can move up and down between 0 and 1 meter. We take this distance and we divide its range by 256 equidistance intervals for the robot arm. Beautiful, and this is it. So if you read here that we are operating, for example, with 256 discrete points or discrete bins, now you know this is simply an approximation that we go from a continuous space to a non-continuous space, simply for simplification. Now, if we have now our action encoding, what is it? It is simple. Let's say we want the arm to move 50 centimeter up, 30 centimeter to the right, and 20 centimeter forward. Now, in our discrete action space, we need to find the corresponding bins for this coordinate. So let's say the bin for the translation is 128, 77, and 51. Just hypothetical numbers. And if you want here for the rotation, you add some different numbers. So you get a string of numbers. And now you know what is the miracle between this string of numbers. They are just giving you the 6 degree of freedom for translation and rotation, plus additional degree of freedom for how wide the gripper opens, the angle of the gripper, or the force that the gripper is able to imprint on a system or any other tool system. You can have at the very beginning 1 if the action is finished, yes or not. So this is the most simple, if you want, embedded control system here of our action encoding robotic system. Yeah, oh yeah, for Ben. I have a young viewer, Ben. Ben, this is for you again. So if you see the string with these numbers here, so very simple. Again, this is a representation of a sequence of robot action in some discretized form. 1 is simply the command to start the action sequence. Then the first 3 numbers give you here a specific position along the x-axis, the y-axis, or the z-axis. Then you have 3 rotational degree of freedom. And for example, if you have an additional amount, this could represent the level of the extension of the robot's gripper, now encoded in some action tokens. And more or less, this is it. Now the robot control system would interpret these discrete values and simply convert them into corresponding continuous movements of the robot arm. This is it. So now you know what are robot actuator action tokens. It is exactly like we know from our human language token, from our vision token. This is just here another pair of tokens. So in essence, the model is taking a high-level instruction in human language, like I say to GPT-4, hey, take this chips and put it next to Google, as you have seen in this little video. It is processing it to understand what action this implies, and it is outputting a sequence of low-level actions in a machine-readable format that the robot can immediately execute. This is it. This is the core of how the vision-language action model works. So you have now let's say the intelligence of our LLM to understand in human words what's going on. Then you have here the vision transformer that tells you, hey, in this image I see 2, 3, 4, 5, 6 objects. And then you have an action model that integrates everything and gives you in almost real time in a closed control loop. If, for example, your chips fall down, the computer or the AI system sees, oh, I have here from an image sensory that here the chips are falling down, so I have to pick the chips up from the bottom, for example. So vision, language, action model couldn't be easier. Now, maybe not so easy is how to train such an AI system, because look, we have 3 transformer systems. We have everything we know about the human language transformer system. We have here the vision transformer system, and we have the robotic transformer system. Now, the good thing is all 3 are transformer systems. All 3 have tokens, and we can integrate those systems. This is the beauty. And yeah, the title gave it away. We have a robot transformer system, and this is here the advanced version 2. Now, to train, we have to understand that there are more or less 2 major components in our robot transformer 2 system, in our model. We have at first our vision language model, where the whole model is based on. And we have the robotic data with 6, 7, 8, 12 degree of freedoms, whatever you have. So first step is here the pre-training. The vision language model used in RT-2 are pre-trained on a vast dataset. Dataset has a specific name. More or less, you just have to know it is about 10 billion image text pairs with about 110 languages somebody borrowed from the internet. 10 billion image text pairs. So you have a verbal description, what is the content of the image, and you have the image itself. And this is what our vision language model is pre-trained on. So this pre-training allows the model to acquire a real good understanding of the semantic, textual, and visual concept. Great. So we have now, let's say, all of the internet, all images of whatever, and we see now, we understand now how the semantic context and the visual context goes together. And now we link this simply with robotic data. Now, as I told you, RT-2, there was an RT-1, and the beauty in RT-1 was they did a lot of experiment and they collected a lot of robotic data. And you're not going to believe this, in RT-2, we're going to use the robotic data of RT-1. You are amazed. Beautiful. So each robotic demonstration that we have now in our dataset is annotated with a natural language instruction from one of multiple skills, providing the model with a practical understanding of the various robotic tasks. Great. We have to have a base model, and as I have shown you in my very first AI Robotics 1 video, we use here PaLM-E. Of course, this is by Google Robotics or Google Brain or Google whatever. They use here their in-house LLM, the in-house embodied system, AI system. So they use here the RT-2 PaLM-E system. This is about a 55 billion parameter system, and in this particular model here, the weights of the robotics dataset are about 66% of the training mixture. Isn't that great? But let's have a look at this training again. So the process of learning this translation from the human language to a robotic action is done by fine-tuning. This is here that I do not show you right now. But before we fine-tune, we have to pre-train the model. And the first pre-training step is, of course, as I showed you, the large data set of internet text and images. This is our pre-training. So the model understands language and vision, but it does not know anything about controlling a robot at this time. So then we add here the robot data set, the data collection. And as I've showed you, it comes from RT-1, and you have all these degrees of freedom and all this tokenization. And now that we have a base model and a data set, yes, as I showed you, RT-1, the data set here, in December 2022, they created over the course of 17 months, more than a year, with a fleet of 13 robots. They collected, recorded, registered, and analyzed 130,000, let's say, movements over 700 different tasks. So they have a beautiful data set that they're going to use now here for the robotic training data. Exactly, the robotic training data set for RT-2 is now based here on this RT-1 data set. Each demonstration is annotated with a natural language instruction, and they decided to go for 7 different skills. As I've shown you with the tokenization in a discrete space, now we have also some discretization of our skills. We just say, hey, I just focus on 7 tasks, actions I'd want that my robot system can do. Pick an object, move an object 1 near the object 2, place an object upright, knock an object over, open a drawer, close a drawer, place an object into a specific form, or pick an object from a form and place it somewhere else. So you see, the training data are extremely detailed for each specific task. Open a drawer, close a drawer. The system has no idea what is a kitchen, what is a drawer. You have to provide the training data, hundreds, thousands, millions of training data for one particular action, that the system learns only this one particular action. Beautiful. So we have this training data here for our robotic data set. And now we have here in green the fine-tuning and the co-fine-tuning. And now that we have the base model and the data set of our robotic data, now we do the fine-tuning. So the pre-trained model here is then further fine-tuned on this robotic data set. We fine-tune the model. So during this phase, the model learns now to associate the task description and the visual information of the base model with the corresponding robot action. So the AI system pieces now those actions together. It has a task, it has some visual information, and it has some robot action, and then it gets another visual information to validate or see if it did move in the right direction or in the wrong direction. So you have a closed loop, and you can do this in real time. And this is the way the model learns here. Then in inference, but we are still at fine-tuning. And then the authors at Google decided to do something very special, co-fine-tuning. And you might say, hey, what the hell is co-fine-tuning? Now they say, to improve the robot's performance, the model is co-fine-tuned now with the data that we used in the pre-training again. But since we have now the semantic content, the visual content, and the robotic action content, we use now to be sure that it is really interlinked on each and every level. We again co-fine-tune this now on the original web data with the robotic data. And they say this helps the model to generalize better, since it is exposed now to both the abstract visual concept from the web data and the low-level robotic action during the fine-tuning. So this is an additional second fine-tuning step they call co-fine-tuning to improve the performance of the system. Again, fine-tuning explained, co-fine-tuning explained. You can do this between different tasks and given some images, the robot understands what's going on. So we have now our RT-2 model. This is an instantiation of our VLA model. It is co-fine-tuned on the robotic trajectory data and on the internet scale vision language task. You know this is beautiful. Now, the main difference to the RT-1 model, if you say, hey, what is the difference, is the RT-1 model did not use this internet-based VLM pre-training step. So now we can kind of validate, hey, how important is it to have here our VLM-based pre-training? So if you go here, here, how important is this pre-training step? Because I could say, if I do not want to have the internet amount of semantic content and vision content, and I start with the robotic data collection and I do the fine-tuning and the co-fine-tuning, isn't this a better system? And the answer is no. If you have this, let's call it semantic visual intelligence already in your base system, so if your pre-training makes the connection between semantic content and visual content, the fine-tuning and the co-fine-tuning improve the performance of this system even further. Beautiful. They did some evaluation. I don't have to tell you that it is great, it is beautiful, it overperforms and outperforms. But the real interesting thing is now, because of the visual semantic correlation, these models will also test on unseen tasks to evaluate their generalization capabilities. And if you remember my introduction video to AI and robotics, where I showed you I would like to focus here on a new spacecraft, the next generation of spacecraft, where we have an AI robotic system for unseen tasks. Because if you enter the atmosphere of a satellite or of Jupiter, you will see something that we have never seen before on Earth. We have no idea what the image that we record with our cameras on board of the spacecraft, what this object is. But if I can extrapolate, try to understand from the complete knowledge of planet Earth, of our human internet, some phenomenon I see in the Jupiter atmosphere, on unseen tasks and have a kind of a generalization capability, this is exactly what I want. And this is now the time to make this kind of mini series here about the new space probe, about the new spacecraft, where we have exactly this generalization, abstraction ability of the system of our spacecraft to learn. As I told you, outperform baseline on unseen task. Yes, pre-training. Yes, you have also these emergent capabilities. They were performed tasks that they were not explicitly trained for. This is exactly what we need in a spacecraft in an environment that we have not been there. We have never seen it. We don't understand what's going on. It is an absolute miracle, the object that we see on the image, but the more intelligence we put into this AI system in our spacecraft, maybe we have a chance that the system can try to deduct maybe some components or maybe some elements and then start a reasoning process. Great. Baseline across all categories, beautiful, beautiful, absolutely great. So if you want to see now a lot of videos and demonstration and everything, this is the web to go to. RT-2 Vision Language Action Model here by Google DeepMind. You have the paper, you have the blog post, you have the demos, you have here the RT1. Have a look at this. There are some really, really interesting videos, but also try to abstract what this system can do with a funny robot in front of a table. And then think what this robotic control can do in a three-dimensional space. If it controls here not a robot arm, but if it controls the thrusters of a spacecraft in Jupiter atmosphere, how it can learn, adapt to how much power it goes to the thrusters, how the system, the spacecraft behaves in the strong wind of Jupiter's atmosphere. The system can learn to adapt to its environment. And this here is now the fascinating interlink between AI and robotics. The complete system learns new data based on the normal, on the basic intelligence we provide when we send off this spacecraft to Jupiter. Anything else? No, this is it for today. But you understand what is missing now is, of course, here. How does the spacecraft decide about the next steps? If it can analyze its environment, if the spacecraft has an intelligence to control its own thrusters, where's the best trajectory given that it has, for example, a complete LiDAR scan of its environment? What is the trajectory the spacecraft should choose to proceed? And we need a robot policy, and this will be the topic of my next video.